Alright, I want to give my bit on behind the bit. And this is basically going to be likely more than one video about, I guess, a documentary about Mr. Bit. And this comes about because I've received so many PMs and questions asking why I debate what I do, and I guess what are some of my ideas based on hardware versus software, all kinds of things that have come up. So I'll try to address as all of that in this video, because I think all of it relates, because it explains really where I come from in terms of what I debate and what I think and what are my ideas based on. So first of all, I'll say that I have come from a hardware world. I used to be a hardware technician. I also used to be a network engineer, and left that for software development. And that primarily came about by asking question after question after question. You know, just why? And I found it to be eventually getting down to the software level, in that things like assembly or machine language, I mean, that finite, the stuff that I call the fairy dust and the hardware. You know, some people don't think of software at that level, but it still very much is. A lot of that has to do, you know, with the firmware instructions on telling controller hubs what to do, so on and so forth. So that's still very much software. And I guess that could go hand in hand in saying why I advocate software over hardware many times, and could give an example of maybe two machines have identical specs, but perhaps one runs faster than the other. And 99.9% of the time, that's going to be because of software. So, not to say you can't increase hardware and things like that, but I say, yeah, you can increase hardware, but that is where I'm going to start into my discourse, if you will, and explaining where I come from. I don't necessarily like the idea of throwing more hardware at things. I think things that should retract and actually use less resources and become much more efficient. And that will pretty much be the first point of what explains the basis of what is behind Mr. Bit's thinking. And a lot of that comes from that people will ask me, well, I'm for this, but I'm yet against this and other things. And the reason that is that I understand we have the reality of what we have today, which I consider, at least for desktops, a CISC, Intel dominated world, and a Microsoft generalized application development kind of world. That's the reality. Of course, we have other types of OS architectures like Linux, BSD, OS X, so on and so forth, and that's why I heavily advocate those systems, and why I also advocate setting OS X free. But I will get back to that in more detail a little bit later on, because we need to get some more history on why that is. So throwing more hardware at things I don't think is always this solution. I think, like I just said, that is pretty much this desktop world that we live in that was set up by both Intel and Microsoft, and it doesn't necessarily mean that's where we should be. So while we could say be here, in my ideas and what I advocate for, we should be here. It doesn't necessarily mean everything here is all bad and everything is crap, but I think people should be aware of a lot of things, and this is why I'm making this video, and because that aware part is what motivates me in technology. When I really got into software development, I was very much always interested in reduced instruction set computing, which is RISC. Now, I will say the lines have become blurred, because even CISC has employed RISC technology, and RISC in itself, some of the newer chip makers have added complexities, kind of getting away from the actual RISC environment. But the RISC chips still to this day still have more registers. Now everybody's going to say, well, what's a register? Well, basically a register is a storage place on a chip that is very, 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 very fast access to the actual execution unit. Okay, what RISC does, the whole premise was based on when an instruction came down, it only used, say, 40% of the available instructions on a CPU. So the engineers that thought up RISC were saying, well, if we're only using 40% of the available instructions, let's limit the chip to those instructions and make the rest of the available space for increased registers. And that actually allowed for a much faster performance because you can get more done in one cycle. Now, that has also its cons, and people are arguing, because mainly back then when it was debated, RAM and doing all the CPU RAM, or I should say CPU memory, was considered very costly, but that has proven not to be the case. So really, in the end, what so much happened? Well, in at least desktop computing, Microsoft comes about with something called DOS, and DOS pretty much, let's put it this way, was in a position that its competition in terms of desktop computing made some mistakes that allowed it to prevail. After all, one of its major competitors was Apple, which had a GUI, but yet it lost market share to a command line interface, and that primarily had to do with software in terms of applications, and which really what the end user wants to have. Now, that wasn't necessarily so much as devastating a market share loss as it was when Windows 3.1.1 came out, and then of course Windows 95. But nonetheless, you can kind of see where things were balancing out. And what this leads into is that the efficiency argument that I say is, it always baffles me the decision that Microsoft made in choosing DOS, while there was other BSD type systems out there that were open source as well as Linux. They could have used that and could have gone to really a multitasking, multi-user type system. But they chose MS-DOS, which is a single-user, single-task system. So we have basically not only a non-GUI, but a single-task, single-user system, essentially taking market share away from other systems that had multitask, multi-user systems, and others that had GUIs. This was a ideology break, in essence, when DOS came out, because not only did it have favorable parts in terms of applications, when DOS was released, it had all kinds of support because it didn't have binding hardware. It was just a software package. It said, well, we'll run generally on what you can throw at us. And that was pretty much what they were going to be running on Intel standards, or what we have the x86 Intel. And basically, x86 Intel leads to CISC. And that architecture basically puts a middle layer of functions. And not a middle layer of functions, but it has a middle layer for instructions, is what I wanted to get at. And it supports higher level languages at a cheaper cost of development than would RISC. Now, RISC could have easily made across the board general compilers, and it wouldn't have taken away from the efficiency power of RISC. It's just that the ideology of the competition of Microsoft was in the mindset of, well, we're tying software to our hardware, and everybody was competing with each other, so they never really had an issue to say, well, let's combine forces and make general compilers, so on and so forth, because they were already competing with each other. You know, they wanted to have one RISC competitor wanted to have dominance over the other, while Microsoft enjoyed pretty much almost no competition within its ideological frame set that it had created. So this generalized computing accelerated and gave more support to the CISC architecture. As it, of course, Microsoft gained more and more dominance, that single user role, not so much the single task as they got to multitasking, but the single user role, while they technically made multiple users, has haunted them still to this day. And that to me goes back to the choices that I think that they were made. Primarily is that if you could ask any Vista security team that works on the UAC, one of the major problems that they had is that applications were used to running in the admin mode, which inherently is this single user mode, even though you could technically have other users. For eons, many people were using this single user role. And finally, when they come to Vista, they want to make Unix-like file permissions and different user level structures. And when they didn't have access to certain kernel services or user space services, the software was breaking down. So that's how it has come to haunt them in that regard. And I consider that an enormous inefficient choice that we're dealing with, and that compounded with, now we'll get into the CISC, which is if people remember, the Pentium chips kept going up and up in cycles, and I think they got up to what, 3-something gigahertz on the Pentium 4, and they were trying to push as many cycles. And the reason that is that while RISC gets more done in one cycle, the software itself is already ready within the way it's written to get itself done. But it is cumbersome because you don't have as many other instructions that you would use in that sense, so it does make software development more expensive, but that could have been solved with compilers, and obviously it happens today where very much of the high-end and enterprise editions are successful. But with CISC, it's running more cycles and it's handling more complex instructions, and that's coming down from these higher level languages that we all see within our operating systems. And it makes forth a cheap software mentality development. It's just like this, it's such a cheaper development, right? That essentially then they're feeding each other, because the more developers you get, the more applications, the more users are going to be wanting to use these applications, which then further builds like this. It's like this. We have this foundation that should have had other choices and things done, and we're building this building on it, and it's starting to tilt because we have so many issues that were overlooked, and business and politics go on, and no one's addressing and say, hey, let's go and rethink architecture, because quite frankly, when you do change architecture, the software has to change, and that's what I will get at a little bit later. So basically you have this handshaking type thing of Microsoft and this Intel and even AMD jumping on board when AMD used to even support RISC architectures. And finally Intel is still getting technically is losing in terms of performance to RISC, and so they're upping their cycles, and finally they can't do it anymore, and they start going to multiple cores. That now leads to a world that we're living in. And that's where hardware jumped a little bit ahead of software. But what's ironic is that machines back in the 1950s used to, and going in the 60s, used to be multiple processing type machines, and then that was abandoned for the 1980s, the popular the uniprocessor type style. So we're back into the multiple processing, and then we have things like what you hear about on YouTube, like symmetric multiprocessing, things that I've discussed before, and it's a lot of that architecture is not really being utilized so much by the software that we have today. So that's why I say it's jumped, in that it comes to the question of, well, we multitask and we also have parallel or parallelization within our software, and this gets into the inherent idea of RISC, which we call pipelining, to get as much done in one cycle as possible. That's parallelization in essence. Okay, multitasking is not so much parallelization. Multitasking is more general computing, and as we increase cores and up the cycles again, you're increasing your general performance. Basically what happens is, as you have kernel level services and user level services, applications that are also executing, so on and so forth, they are all being shared over the multiple cores or multiple CPUs, and that in itself is what you see and debated in many YouTube videos, like who does SMP better, because that will give you general multitasking performance. But most of the time I would say that 80% of the users aren't really multitasking or pushing the multitasking barrier, in that you don't have too many people that do a tremendous amount of compiling and then encoding and let's say streaming, and then maybe working on something else all at the same time in true multitasking form. See, people usually just go to their email. They may leave their email application up and they'll go browse and maybe listen to music. That's not really pushing the tasking, because there's not a consistent instruction set flow that's going. So those instructions that have finally come and what is in memory simply becomes a lower priority and a lower interrupt. And of course, when nothing is happening, there are no interrupts from it. So you're not essentially really multitasking in that sense and pushing the envelope. You will definitely see performance gains in multitasking when you do push it as technologies get better. But people, what also they don't realize is that everybody gets excited about increasing cycles and throwing things in. And what is truly sad is that Intel becomes a standard for measuring power of other chips. You know, people say, well, if you're not 2.1 gigahertz, you're going to be absolutely slow, and that's not necessarily, that is not true at all. It's a fallacy. That's the inefficient world that I argue against, that we live in. you go that fast because of the architecture it has. Today, Intel uses all kinds of technologies to get around that middle layer that takes these high instruction levels to decode it, which RISC doesn't have to involve. And the lack of less registers versus more registers and so on and so forth. And they make all of these types of new technologies. What I find ironic, instead of increasing cores, what they do is they increase cycles. And that is basically getting back to the whole uniprocessor thing of where they were increasing the cycles. Well, I don't know if anybody's ever thought or even questioned that how far are they going to push these multi-processing unit cycles up. They're eventually going to pretty much run into the same thing. They're running into pipelines, they're running into cache misalignments. We have major bottlenecks within RAM and front side buses coming off of these CPUs. That's why you see so much efficiency loss as we're adding these processors. Now, especially when it comes to parallelization, there's a law called Amdahl's law, which will what it's designed to do is predict the maximum efficiency for parallelization with how many cores that you have. And it basically shows as you add cores, you'll get to a point to where adding cores does nothing anymore. And because the efficiency loss is, and the overhead of running such an architecture is so overwhelming that there's no more gain. So this is the world that I argue against, and why I'm primarily in most of my arguments will argue against Windows and Intel, and that's why. So it will answer, I hope, those questions that I have. That now when I go in other arguments where I'll correct people, and that is primarily based on I want people to understand the technology. If we don't understand the technology, we can't understand what I'm even talking about within this video. Where you first have to be brought to the same level of saying, well, what's going on, so we can further debate what the actual technology is, rather than going off of propaganda and so on and so forth. So that's why I do that. Once we've established an understanding of technology, then other people can jump on board and then start questioning these types of things. So I've basically covered Amdahl's law and the massive inefficiencies that we have within multiprocessing. The other massive inefficiency comes with the software that we're running. Because we run with this generalized software that we have, most of these things aren't even multi-threaded. So they in themselves just represent a task on the CPU. They're not really even having any type of parallelization. And parallelization is where the real speed comes from, guys. It's not a general shifting of tasks bumps you very little. You want true performance, and everybody, especially like the Windows arguers against Mac and bragging about games and I throw all this hardware at it. While I do it myself, that is the real world that I have to live in, because I can't have the wishful world that I know is in itself real, but it's not executed in terms of consumption for the market or anything that I could get my hands on. So we basically have these people that argue and argue and argue, and yet software has done nothing to actually give you real speed. And that's what will lead me to like this latest deal of videos I'm seeing with like Nehalem. Intel has come around and all this other stuff, and I laugh at that because, quite frankly, what is the big deal? Yeah, Intel's Nehalem is faster than its predecessors, and unfortunately AMD had some problems before, but they're coming right back with their Shanghai, and I hope that they do well. But that said, having two threads per core, everybody's, wow, look at this. What if I were to tell you that UltraSpark has had 8 threads per core for many years, and in many systems you can get 64 threads in total? Now you're okay, well, what's that all about? Well, if the software already is not multi-threaded, what benefit is it going to get? You're not going to get faster parallelization. It's not even going to be executed. It's actually coming off as a gimmick. Yeah, I'm offering you 2 threads per core, but if your software doesn't use it, it's like, yeah, you have more hardware than what your software is actually going to be using. Okay? And this is where Sun came with their ideology, because we can get away even from just the fundamental RISC, just the RISC chip, but keep its ideology and making things simplistic and getting more things done in one cycle. And that's what Sun was after. They're saying, man, we'll give you a lot of threads on what our core can execute, and But you know what the catch of that is? Is that the software has to be written to read those threads. And then you see all these benchmarks where Intel gets out there. We just spanked the living crap out of Sun and all that. No, you don't, Intel. And what's funny is that they don't even bother doing fair benchmarks. All they do is single-threaded tests against the UltraSpark chips, which the Sun chip is not designed to do. It's not going to be very fast because they're running number one on lower cycles, and they're not built for this single type of thread coming down. So Sun has vendors that write software for it and that runs extraordinarily fast. But see, that would humiliate Intel's architecture. It'd be absolutely humiliating. Because once you start putting a thread system on it, that threaded software could only utilize the very few threads that Intel had, but it would maximize the amount of threads that UltraSpark would have and would blow Intel out of the water. It would use less cycles and be much more efficient. Wouldn't have all this damned overhead and all this technology that Intel builds just to get over itself, just like with the multi-threading that Intel's trying to do with the Atom, just to try to compete with the RISC, with the mobile computing and embedded RISC chips within those markets. They're suffering in that sense to try to get over this hump of pre-decoding. And that, of course, is the CISC inherent problem. So this is where I've established pretty much this hardware and software generalized computing of this building of when is it going to hit another ceiling and say, well, we need to rethink things. Obviously, Intel's saying we're going to start putting threads in our cores, which Sun and many other RISC vendors have tried before, but to be competitive, they have to support this x86 architecture and many times single-threaded applications just to stay competitive. That we go back to the threads. Because I think that's the answer, is being multi-threaded and finally getting these applications to run faster and getting true parallelization. And that's what I argue. That's why you see me advocating RISC. And the operating systems that advocate, like Linux and BSD and OS X, are fully capable and can manage such a thing in a far more efficient fashion than what we're seeing Windows, because Windows really doesn't have an interest so much in doing that, while they have had systems like my favorite Windows system of all time was Windows NT 4. That could actually run on RISC. It's not taking away from Microsoft and saying they're not capable of doing it. It's just they have this legacy barge, if you will, and they're like this tugboat that they have to tug this massive 132 legacy, because that's their ideology. Support as much as they can. So that in itself, if they can't convince everybody to upgrade as fast as they want, have to continue to support this stuff, and therefore have no interests in their model to switch as fast as getting to multi-threaded type stuff or more efficient type computing. So that essentially is where I come from. You can also tie this into, let's say, my own style of programming. Many people always ask me, what software products do I have out there? Well, I do have some that can be sold to multiple vendors. But most of the time what I write is extraordinarily custom. That's what I believe in. I can't tell you how many customers I go to, they say, well, yeah, we bought this product, but I wish it could do this, or I wish it didn't have this. That's where I come in and say, your wish is granted. I'll write you the application, and I usually am able to pull it off for close to the same price that they paid for the product. That's something that's kept me in business. Something why I think word of mouth has done some good in that sense, but not so much talking about my business, but that's my ideology. Is that if I can customize things and make it efficient, I'm customizing it to you. You're going to use everything in it rather than you buying something that you're not going to use. Therefore, that efficiency loss. Because sometimes you can buy whole packages of software, and a lot of that software can be contingent on a feature that they built, but you may not use it, and so many services are dedicated for that, and you're just flat out not using it. How much inefficiency is happening there? Stuff like FireWire and USB, like USB's middleman, and their shared, if you want to call it, their shared controller and bus, basically, versus FireWire, which is peer-to-peer. To me, USB is an efficiency loss. It's a standard and it's cheaper and all this other stuff. Then let's go back to even software with object-oriented programming. While there's many benefits object-oriented programming, when you get to the finite, you get to this fixed template that you can't break. And so when you go and you see, while it's more expensive as a development, you can get more custom and you can access more specific let's say, even registers or even memory addressing than you would if the finite object-oriented template that you're using does not adhere to those points or even as efficient, let's just say, in addressing those things. While it is cheaper to do that, it's not necessarily as efficient. And there's many computer engineers that don't like object-oriented computing and argue against a lot of what I'm saying in terms of these basis templates that you can get caught up in. You can then, again, it's like this building that we're building up and how we're having this desktop computing. And so those are the things that I argue, and I hope that explains where I come from. And that's why I love to do these educational videos, to try to explain people technology. And maybe one day, I highly doubt the market will change just because people become aware, because we have to obviously use applications. Microsoft proved their model was market friendly, but I would say that many mistakes were made by their competitors. And had those mistakes not been made by Microsoft competitors, the world wouldn't be as such. All right, but now that we're with the world that we're dealing with, I think we have to wait for that to either hit a severe wall in progress to where its competitors can then gain software, and that's why I talk about setting OS X free. That OS X can still run on RISC architectures. It could partner up with other chipsets and things like that, and actually offer maybe to other niches and things like that, or Linux or BSD, anybody, to get more software out there. The idea that I'm getting at is we got to shift our general computing, what we're using now, get it multi-threaded, get it out there on other operating systems that can maneuver easier to these other architectures and more efficient architectures, so that end users who really don't care about what I'm even discussing, because all they want to do is make sure that the damn application works and they can get what they need done, they'll be able to have that as an option and have better, most of the time, better features and results than what they would have currently. And that's why I fight so hard for software platforms, for people to look at other software platforms, why I advocate setting OS X free. I'm thinking well beyond just Apple. I know people who like to defend just Apple. I'm thinking well ahead of that. It's like what I've just explained. I ask these questions and say, well, this is a great alternative, and I love OS X as a operating system because it already in itself has an inherent large user base versus some other operating systems that I'd like to also see flourish as well. So that's the way I see things, and I hope that answers most of the questions that people have been asking me. And again, any specific things that you would like to ask, because I know I've left out some things that I'm now just thinking of, like where new architectures are coming up, which are massive parallel processing, things like that. And that's not so much the hardware that is significant, it's the way the software is written. And NVIDIA's got like this personal supercomputer that they're using. They talk about 960 cores, and the reason why they're able to pull this off is because of the way the software is written. And that each of these, if you want to call it pipelines of this processor, has its own dedicated memory, its own so forth, going up on the execution process. And the software is written to be broken up and run in parallel. Okay, so just imagine like this application is allowing itself to be split up, and then this instruction coming out, rather than just one straight line. Boom, it breaks up and then runs and comes back like that, versus like this long thing. So I'll post a link to that, because I think that's also another possibility to go massive parallel processing, but also utilizing threads. And that in itself is a thread. It's all really the same philosophy, but kind of using different types of addressing that philosophy of dividing software so that it can be run in parallelization. So that's pretty much the behind the scenes of Mr. Bit's thinking, and where I come from, and why I left hardware for software. Because from the levels of the fairy dust to what you see in high-level programming and operating systems, and how all of that can significantly improve just efficiency and power of computing versus what hardware, because we could simply just run on slower hardware and get the speeds that we have now, just by addressing these blocks of inefficiencies that we have. Anyway, thanks for watching.